All right, this is like take 4 of this video because I keep sneezing and other stuff, but we're doing something, we're just talking briefly about pulleys and simple machines. Okay, pulley is actually a type of simple machine, but since we're mostly talking about pulleys, I thought we'd do it here. So what do simple machines do? They reduce the force needed to complete a task. Okay? The best examples are pulley, lever, inclined plane, screw, etc. So how do they work? And I guess I should say, how do simple machines work, not just pulleys? Um, and when they're used properly as simple machines, what they do is they reduce the amount of force necessary to do something. Okay, the amount of force you need to put into it. All right, let's think of 2 examples. Have you ever tried, if there was an object that was too heavy to pick up, right? So it's like a 50 kilogram object that's 110 pounds. Let's say that's something you can't pick up. All right, and you need to get it into the trunk of your car. Now you could get a friend, help you out, your parents, 2 of you could do it easily, whatever. All those different ways you could unpack it, put it right, all these different things. But you need to get it in there, and you're all alone, no one around, nothing like that. What if you got a little ramp, and you push the object up the ramp instead of picking it straight up? Okay, you've reduced the amount of force you need to get it to move. It's easier to push something up a ramp than it is to lift it straight up. Okay, that's always true. But there is a cost to that. It makes you move the object further. Straight up is like a short path, but up a long diagonal is going to take you more distance. So essentially, simple machines trade less force for more distance. Okay, a lever does the same thing. Think about a bolt, right? You can use all of your strength to try and take a bolt out or something like that, right? Unscrew a bolt. But with a lever, okay, you get a wrench, you put the wrench around the bolt, and you're now strong enough to move it. Now the difference is you got to move in this big circle around it, right? That's the cost. Now you'll notice, right, that cost, like when the bolt is now like loose and you can move it with just your fingers easily, you stop using the wrench because now it's faster to move. You don't have to move it as far. But that's the cost always. Okay. Now, a screw, or just bring this up. A screw is just an inclined plane that's looped around a central thing, right? That's all it is. If you actually look at like a screw, like the little screw thing is just an inclined plane rotating around it. All right, and that decrease in necessary force is called mechanical advantage. Okay, so if it takes you 50% as much force to do this to do the task, then you have the mechanical advantages too. All right, that's not the main focus of this. We're looking at pulleys. Okay, and pulleys can be used as a simple machine. They can also not be used as a simple machine. So let's look at 2 situations where someone is using a pulley to raise something. So we got this object, right? And from what we know, or we should know, right, there's a force of gravity down on both of these objects. Right? And in order to lift them, right, we need a upward force. Right? In this case, this upward force is directly the tension. Okay? Now, one thing you have to understand with pulleys is that, right, in a tension, the rope is always pulling on both ends. Now, in a pulley, that actually means it's pulling on the pulley and making it spin. Like you've all done a pulley where like you start to pull the rope and the pulley starts to spin. That's happening. Even if it's not spinning very fast, that's definitely happening here. And in fact, the tension pulls on both ends of the pulley, on both sides of the pulley. So we actually get this tension here. And then we think about what's actually happening, right? To lift this up, I need the force of the pull down. Now in this particular example, right, if I want this to rise, tension has to be right here. Tension minus Fg has to be greater than or equal to 0. Which means that F pull, right, because this is the same tension here as it is here, as it is here, as it is here. It's actually, if the pulley has a lot of mass or friction, that's not true, but most pulleys are pretty close to massless or frictionless. We'll deal with when these tensions aren't the same, but let's assume these tensions are the same. F pull is going to be greater than or equal to Fg to lift. That makes sense to me, right? So this particular setup has no mechanical advantage. Okay? This pulley is not being used as a simple machine. This pulley is just redirecting the force. It's changing the angle. And the reason it does that is because there's actually another force here. The ceiling is pulling up on the pulley, right, to counteract these two tensions that are downward on it. So the ceiling's actually pulling up. So the ceiling and the pulley combination are redirecting the force, that your pull, to be an upward tension force. Okay. Now, what if instead we set it up like this? So now the object is hanging from the pulley, and we're pulling up here. Erase that. Okay, so F pull is there. That's the same as the tension, right? So we've got tension here. Oh, I should say, sorry. There's another, like there's the tension force also on your hands here, right? Every force equal and opposite. Those two forces are opposite, right? Okay, so there's a tension force here on your hands. There's also a tension force here. There's a tension force here. And there's a tension force there. And then there's also the ceiling here, right? Okay, so these two have to be opposite and equal, or the end of the rope would be like moving, like where it's, or whatever it's, however it's attaching would have a net force, and we don't want that. It would fall. So this upward force here, right? And maybe I should erase that upward force now. This upward force. So this pulley box combination has two forces upwards. It actually has that as long as 2 times the tension minus Fg is greater than 0 or equal to 0, it will lift. All right, so it will rise as long as that's true. So all of a sudden, wait, pull is equal to tension. So all of a sudden, 2 times the force of the pull has to be greater than or equal to Fg. So this basically doubles my pull. My pull has only got to be greater than or equal to half of Fg. And that's the mechanical advantage. Okay, it's because these two tensions are both upward on the block, right? There's always 2 tensions on the pulley, but because the pulley is attached to the block, both of them are pulling up on this whole thing. Now you might think, wait, isn't that just like make everything easier and it's free? So let's imagine something. Let's imagine I pull down and I move this whole rope down 1 meter. This thing goes up 1 meter, right? Perfect. But if I pull this up by 1 meter, the box actually doesn't rise by a whole meter. Okay, it actually only rises by half a meter. And here's why. Okay, if I'm thinking about it, this loop, right, here's our starting point. And I basically want to turn this into this loop. It's not a great drawing of it. It's not that much shorter. To that, right? So this becomes that. All right, what have I done? I've changed this point by 1 meter. Okay, but in order for that to happen, I actually only have to shrink, right? So let's just say this was 2 meters and this was 3 meters. Okay, so I guess now I've risen up here. So now, right, if I raise it up 1, they're now equally both at the top here. This whole string is still 2.5 meters long, is still 5 meters long, which means this distance is 2.5 meters. Uh-oh, my PowerPoint crashed. Bear with me here. All right, we're about to redraw that again here. Hopefully you got all that information about the force stuff. But maybe we can redraw it here. So let's just change some number. Let's say this is 4 meters and this is 2 meters. And I want to raise this up. I raise it up 1 meter on the end. So I pull for a distance of 1 meter. Okay. Now, instead of it being 4 and 2, right? I'm now, and this distance right here is also 2. I'm now at right here's still the ceiling. This distance is now 1 meter. Okay, that means that this distance, right, and this distance have to add up to the same thing. These two and this And the only way for that to happen is for this to be 2.5 and this to be 3.5. Right? 3.5, 3.5. And the total height change, right, is, and the total length of the rope is still 6. But that means the box has only risen up half a meter, right? The box is here, 3.5 meters down. The box was here 4 meters down. So I've doubled, like I've got a mechanical advantage of 2. I've doubled how far I can pull it up. Or I've doubled the force essentially, or have the force needed. So I've doubled the effectiveness of my force and have the force I need. But I've only got, and by doing so, I've only moved half the distance I move my hands. All right, so that brings us to the bosun's chair. The bosun's chair is a way of raising somebody on a boat. A bosun is a position on or a rank on a boat or something like that. A position, I don't really know, not important. Okay, way of getting themselves up into the rigging up there, the crow's nest, whatever. I don't really know what part it is. Okay, here's the deal. You have a big pulley up at the top, and you have a rope hanging down, and the rope goes over the pulley and attaches to a chair. And this is how I usually draw it. You can draw it however you want. And then there's a person sitting in this chair, right? They're sitting like this, and they're grabbing onto the other side of this. Okay. Now, think about the forces that are in place here. We've got hands pulling down on the, right, which means we have tension going up. We have tension down here. We have tension downward here. Right, there's still whatever force is the force of the ceiling or the force of whatever that's up there. And then we have another force here, upward, a tension force upward on that seat, on the person seat combination. So if we just look at the person, just the forces on the person and their seat, I'll just draw the person here. We've got a force upward here, a tension force there, and a tension force. That's not what I meant to draw. A tension force here. 2 tension forces upward on the person. So I'm looking at the F net. Oh, and of course we got gravity. I should have. Can't forget that one. So for the person, the F net equation is 2 times the tension minus Fg. If they want to have an acceleration upward, let's say they want to accelerate upward at 1 meters per second. Let's give ourselves a mass here. Let's say the mass is 60 kilograms. And the acceleration we want to go is 1 meters per second squared up. Right? I now need 60 times 1 to equal 2 times the tension minus 60 times 9.8. 60 equals 2t minus... Why is it... guys, I'm sorry. This is crashing here. I don't really want to start it over, though. Here we go. This time it's going to pull it. Nope. All right. Fudge. I don't really understand what's happening here. All right. Anyways. Person. Been over. Right. It's attached. Let's just attach to them. We've got T, F pull, T, 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 Fg. On the person, we've got F net equals 2t minus Fg. Right, we said that the acceleration we wanted it to be 1. The mass was 60. So this is 60 times 1 equals 2t minus 60 times 9.8. So 60 times 1 equals 2t minus 588 newtons. This should just be 60. I don't know why I didn't simplify that. But we add it to both sides. We get this is 648 equals 2t, which means tension has to be 324, which means the pull, the F pull, equals 324. Now, That's substantially less, right? You would, and normally in order to pull yourself up, you'd have to use 588 newtons to do it. So the Bosun's chair reduces the amount of force needed in order to pull yourself up. That's the goal of it, which makes it a simple machine. Okay. Now, a lot of you are probably wondering, why do they have to pull themselves up? Right? Why can't we just have this situation where we got, right, Bosun's chair. Here's dude sitting in it. This is a terrible job. Right? Up. There's my pulley. Down. And then someone else is pulling them right here. Right? Well, now if we just look at them, there's only the upward tension force and the downward force of gravity. Right? So the F net doesn't work. But let's think about the distance thing. Right? This is the key thing, right, for a simple machine. If this person pulls down 1 meter, then the person in the Bosun's chair rises 1 meter. Right? Has to. But if you think about the person doing it themselves, so we got the person, that's not what I want. We got the person, arms out on the rope. Okay? If they pull down 1 meter, right, that means this distance, I should measure that distance total. This distance of x, if x decreases by 1 meter, actually I'll say d, I'll say d. D decreases by 1 meter, right, so this distance is d, this all the way across. The whole rope distance is 1 meter. If d decreases by 1 meter, then each side of this, d over 2, d over 2, d over 2 decreases by 0.5 meters. So they've only gone up half a meter. Okay, that's the cost. All right, sorry about the mistakes there, but